Welcome everyone to this mic-free wave webinar. I have the pleasure of presenting our state-of-the-art wave modeling software, which we have been developing for the past few years. It's a three-dimensional phase-resolving wave modeling application, and it is being used for R&D and consultancy projects. Let's first talk a bit about who I am. My name is Joachim Bach. I'm in DHI Denmark, and I've been in the ports and offshore department. I've been running previous training sessions on mic-free wave FM, and I've been involved in the development of this three-dimensional wave software. And I've been together with DHI for the past 1.5 years. So let's go, so that was briefly about me. Let's go on to the agenda for this 1-hour webinar. First, of course, I have this small introduction. Then we'll go and dig a bit more further under the surface and look into the actual formulations of the software, some of the scientific documentation, talk about how we have implemented the Navier-Stokes equations. Afterwards, we'll go and talk about these features that we are or that are currently implemented in this state-of-the-art software, and we'll see some of the validation cases. Then we'll talk about coastal flooding, and I will show some pictures of the software working. Then I'll also briefly talk about our course in October. So what is mic-free wave FM? Well, it is a specialized CFD model for three-dimensional waves, meaning that we are resolving both the horizontal and the vertical dimensions. It has an easy and user-friendly guided user interface where you can fast and quickly set up models, which allows you to error check your setups on the way. The model has been implemented with a flexible mesh discretization, allowing complex geometrical and bathymetrical features to be represented accurately. Then the engine code has been highly parallelized, meaning that we will experience speed up as we try and distribute the computational load on multiple cores. And finally, we have also introduced some of these coastal flooding phenomena, meaning that we are able to resolve highly nonlinear effects such as overtopping and flooding. And we will look a bit more into detail about that later on. Personally, I think this is quite a game changer in the market, and it is a sort of specialized CFD model, you could say, in the sense that it's not an actual open foam model, but a different way of handling some of these highly complex problems. But we will look into a bit more detail coming further. So first of all, I will try and help guide you and try and imagine that you have access to a wave modeling tool that has no physical limitation in the wave height, in the period, in the depth. There's no KH limits, and it is able to handle three-dimensional porous structures where we are actually trying to resolve some of the flow, or approximating the flow through using porosity models. It has a very fast and easy workflow for specifying all the sponges and the porosity settings necessary for setting up a numerical model. I myself would say that it is one of the most user-friendly of all of our models, and is very robust in the generation of a numerical model. it is fitting within our general mic suite of software and our mic 21 mic 3 FM models. So if anyone has experience with that, then they will find that this model is easy to jump right into. And finally, the feedback on the GUI has been worked on a lot. For instance, when you're trying to specify wave generation zones or porosity zones. And this has been proven throughout consultancies and research and development, where we have user feedback stating that it is actually user-friendly. Furthermore, we are able to robustly handle some of these most challenging aspects, such as wave breaking, nonlinear wave transformations, and overtopping cases, something that we haven't been able to do previously as robustly as now. And especially these overtopping cases have been investigated quite extensively. Yes. So with this software, you will actually be able to simulate both the cases that you are used to simulating, such as wave harbor studies, but you are also able to simulate some of these very nonlinear phenomena as wave overtopping, nonlinear shoaling, diffraction effects, reflection effects. And previously, with some of our mic 21 BW models, we would have some limitations on the water depth, which in this model you don't have. You don't have any limitations on the water depth. It is solving the three-dimensional Navier-Stokes equations, and it is capable of solving any wave fields, such as short wind sea, long swell seas. We can even handle tsunami waves, and of course, all of the nonlinear transformations happening in the actual swath zones as well. It would also enable you to simulate three-dimensional kinematics, so you would have access to the three-dimensional velocity components of u, v, and w. And of course, you could try and simulate some of these porous or submerged breakwaters for that case, where we have wave overtopping happening. And that is just scratching the surface. This software can handle a wide complexity of scenarios, which all of them, of course, I can't go into full detail with. So that is short what mic 3 wave FM is. Now let's go a bit further and dig into the equations. So what we are actually solving is the non-hydrostatic Reynolds-Average Navier-Stokes equations, consisting of continuity and momentum conservation in all three dimensions, where we have a description of the free surface with the sigma following a height function, meaning that we have a single valued description of the surface height. We have implemented this with the K epsilon turbulence closure, and we are of course solving the equations on using the finite volume method on a cell-centered scheme, where we are using the projection method developed by Turin for solving this pressure velocity coupling arising from the incompressibility assumptions. Then we have implemented the software with a shock capturing HLLC Riemann solver, allowing us to reconstruct the intercell fluxes in areas with discontinuities in the surface elevation, such as cases where this will happen is when we see waves shoaling up and breaking. In those areas, we will introduce discontinuities in the surface elevation, which is handled by this HLLC Riemann solver. It is allowing for quite robust simulations, and it is I would say, one of the key features of this new software, where we are or allowing us to take the extra step and actually transform waves all the way to the thrust zone, where we have all these processes of wave breaking, undertow profiles, longshore currents, radiation stress gradients developing, which is actually possible to simulate using this software. We have also implemented, in order to capture this overtopping effects, we have a flood and dry algorithm, which allows our surface to briefly dry out in places where we have bathymetric changes or increases. In those places, we only solve the momentum equations and disregard some of the continuity. When we have cells that are very, very thin, meaning we have a very thin layer of fluid. So that's a bit about the numerical solution technique. Then let's go into some of the main features. I have included this picture from one of our simulations, which you can also find online, where we have an overview of all the features that is available within this software. We can see waves coming in, approaching the breakwater from angles. We see the interaction of the waves when they approach the angles, the development of these reflection patterns. We see the rundown of the waves when it overtops the breakwater and goes in and disturbs the surface elevation within the harbor. In the distance, we can see the waves shoaling up on the beach, drying out and retracting again before the next waves are coming on. And we see, of course, this wave disturbance within the harbor. Everything is three-dimensional, and actually, if we go one step further, we can see that everything's been in a flexible mesh fashion, where we can also see that there's been a trench dredged within the harbor, allowing vessels to exit the harbor, and we can investigate some of the circulation and wave phenomena arising from this dredge channel, if we so pleases. And of course, since it's a flexible mesh, then we can easily resolve all of these highly complex bathymetric features, and it allows for a fast and relatively easy creation of a mesh that is sensible. Now let's talk a bit more about some of this wave breaking. As I mentioned before, we had introduced this HLLC Riemann solver, which allows us to transform waves all the way within the thrust zone, even through wave breaking, meaning that we have no separate wave breaking model as some of our other software. We are actually trying to solve the Navier-Stokes equation. And of course, a bit theoretical background about wave breaking is that wave breaking occurs when the particle velocities exceed the phase speed of the wave. And we have, usually in a beach, we have a period of nonlinear shoaling where we have set down effects of the waves, followed by a wave breaking and setup, and then a bore, which is where we have the broken wave transported throughout the surf zone. And I've included here some snapshots of the wave breaking, and just after wave breaking, here we are actually looking into the very famous Ting and Kirby 1994 test case of wave breakings, which we will also look into a bit more detail in a short while. Then some of these features, again, just to describe this, is that it is a fully nonlinear, fully dispersive surface gravity wave modeling suite. There is no limitations on the wave height, there's no limitations on the water depth, and the three-dimensional discretization allows for kinematics to be extracted underneath the waves. We have this comprehensive, stable, and user-friendly wave generation interface where you can easily specify different wave generation zones. You could have multiple wave generation zones, allowing you to easily try and introduce both sea and swell waves coming from different directions. We also have a fast and easy workflow for specifying sponges, sponge coefficients, and also porosity zones. Like sponge coefficients, you are interested in doing quickly because you need those to dampen some of the unwanted reflections from your domain. Porosity zones are mostly wanted in cases where you have some of these porous breakwaters, and also in cases with submerged breakwaters, or if you have wanting to try and model some steep wave or walls or scenarios like that. You could also try and imagine that you had some very detailed, for instance, wooden piles driven into the seabed at some places. Those you could also try and model with a porosity zone, which we have had quite the success with previously. I should say that the porous flow is approximated via the Darcy-4 equation, where we have different calibration coefficients for the turbulent and laminar resistances experienced by the flow as it goes throughout the porous area. When we try and think about the computational time of the model, this model is actually quite much faster than your typical CFD volume of fluid method. Compared to a general CFD volume of fluid, we are performing significantly better than those, because we are resolving only the necessary water regime that you are interested in, and we are not wasting computational time on empty cells above the surface elevation. So this, talking about speed, computational speed, the Mach3 Wave FM is highly parallelized using an MPI system. It has an easy interface with other mic projects such as Mic21BW, Mic21SW, MA, and Mic Flood. We have you have the capability of introducing when you are trying to downscale some results. You could imagine you had a Mic21SW model on a regional scale, trying to transform these nonlinear spectra. Then you have an area of interest. Here you could set up a Mach3 Wave FM model forced by the spectra that has been downscaled from the Mic21SW model, allowing you a highly accurate representation of the area of interest or the actual wave field that is going on. We have tested the MPI parallelization, which I will also show in a second, on 320 cores, which has shown a superlinear performance where we have a fit into faster pass of the memory, as this helps really speed up the process of the computational time. And the Mach3 Wave FM model has already been tested and validated quite extensively during the development phase, and also through activities in commercial projects and in research and development activities. All right, so let's talk about microwave FM compared to other modules. So first of all, microwave FM is not a volume of fluid method. We are not trying to resolve some of these splashing phenomena that you can try to resolve using a CFD volume of fluid method. When you're trying to model, let's say, overturning plunging breaker, we cannot resolve the actual overturning wave as we are describing the surface elevation only using a height function, but we can represent waves such as surging and spilling type plunges. But these slamming type lows, splashing, spray, those are for volume of fluid methods, open foam models. It is not a microwave FM usage. There are other models similar to microwave FM. Some of these are the swash and the NHO wave, which you can look into more detail using these links given here. These are both open source. They are Cartesian grid, meaning no flexible mesh and no guided user interface. I would say that the NH wave model is the one most similar in the implementation to microwave FM. They are quite similar in their descriptions of the surface elevation and the projection method, but they vary on other aspects. And for the interested listener, you can try and check out these following these things. So next up, let's talk about when to use microwave FM and when to use Mic21BW. So microwave FM is a fully nonlinear, fully non-hydrostatic model, meaning that everything that Mic21BW does can also be done in microwave FM and more. But there are cases where you would want to use Mic21BW since it is faster when you try and look into, let's say, your typical harbor study where you are only interested in some of the wave resonances happening throughout the harbor. In those cases where you don't have deep water waves and you have only weakly nonlinear waves, then you could get away with a Mic21BW, which would be computationally cheaper, and it would allow for faster modeling of some of these wave resonance studies. But in cases where you are having overtopping waves going into the harbor, deep water waves going through channels, and really highly nonlinear breaking waves, then I would suggest you to use the microwave FM model, which is also parallelized better than the Mic21BW and has some of these fully nonlinear flood and dry effects, allowing you to overcome some of the limitations between Mic21BW. Also, you would allow you to see some of these wave kinematics, and you could try and study, well, actually all wave phenomena known so far. So to sum up, you would use Mic21BW when you are trying to see these standard port agitation simulations. Also, when you have where nonlinearity is not an issue. Of course, Mic21BW can handle nonlinear waves, but it is only up to a limit. And also, if you're looking into really large areas, there you could also consider using Mic21BW. Since even though we have this highly parallelized mic-free wave FM. It is still a high resolution model. It is not a regional model. It is used for more small scale applications. But you can use it also for doing some of these deep water wave transformations, where we have really deep water, so large KH values. You can also consider cases where we have these complex three-dimensional problems with waves interacting and breaking on different directions and spreadings. Actually, also some of the cool strengths about mic-free wave FM is a capability to model overtopping. That is something that we have seen a lot of interest in, and that is something that we are quite proud of, that the model is able to handle these overtopping cases. And of course, if you need some of the wave kinematics accurately, then you would rather use a mic-free wave FM model than a mic 21BW model, since you are not limited by the hydrostatic pressure assumption in the mic 21BW. And again, if you are considering some of these, for instance, submerged breakwaters, then you would also consider these mic-free wave FM. So let's look into some of the validation cases that we have been doing. So to ask, can we trust this model? Is it trustworthy? So there's been going on a lot of validation of this model before release. We have run it through some classical tests, including the Kirby test of wave breaking. We tried the nonlinear shoaling over a submerged spar. We have also tried some of this porous dam break comparisons, and we have done some overtopping comparisons as well. So we will look into a bit more detail here in the coming slides. So here, first of all, we see a comparison of a study we did for Total, where we have kindly run many single wave, extreme wave cases. So we see measurements on the left and the mic-free wave FM module so measurements are in black and mic-free wave FM is in red. We see quite a close comparison. To the right, we see a traditional CFD open foam model, and we see that both models are performing quite well, actually. Here we see a wave train coming together before collapsing into a single breaking wave. So it's an extreme wave case scenario. And we can see that actually in the bottom left that the mic-free wave FM captures the crest elevation quite accurately, as even more accurately actually than the CFD model does to the right. So we have also done some speed tests. Here we are considering a three-dimensional basin, which is 14 times 12 meter. It's actually our basin here in DHI Hørsholm, where we have tried to run mic-free wave FM on Linux with 300 cores and an MPI. Here it took less than 1 minute to compute. We had a time step of 5.5 milliseconds, a discretization of 5 centimeters in the one of the horizontal directions, and a discretization of 10 centimeters in the other direction, and a vertical discretization of 9 layers. This is typical application values, although of course they vary based on your needs. But that totaled in 300,000 events, and it took less than 1 minute to compute this on a Linux machine with 300 cores, while the open foam with WAF was 24 hours on the same 300 cores. Here we had also had to refine with 4,500,000 elements, and we can before we got similar results. And we can see some of the results that we have on to the right for some of these simulations. And we can see that actually microwave FM captures the nonlinear wave train shielding quite accurately. Next up, we are looking into the wave breaking of Ting and Kirby 1994, where we have a regular wave train shoaling on a beach. So here we can see that we capture actually the wave breaking point quite accurately, and that we are capturing, if we see to the right, we have some undertow profiles where we have C happening, the point C, the point C is during the wave breaking, where we have a bit smaller or bit worse comparison, but actually still we're capturing the undertow profiles quite accurately, considering that we are using this surface height description of the surface elevation, and that we can't really resolve some of this overturning effects when waves are breaking. So that's actually quite impressive that we can capture these undertow profiles that accurately. And we see that set down and setup effects are captured also reasonably satisfactorily, I would say. We see that the red points, of course, are measurements, and the black point or black lines are the mic-free wave FM simulation. All right, so this was some of the wave breaking where we are seeing the performance of the HLLC Riemann solver in action, and we see that it actually allows us to capture the breaking point quite closely. Of course, we have some of the steepening wave profile that we could perform better, but maybe that would be resolved if we had finer discretization. This case is also presented in the validation report. Next up, we have some of these under submerged or a tsunami induced by submerged landslide. It's an experiment that has been performed by Init and Grilly, and we have compared this with the mic-free wave FM black and hydrostatic mic-free model as the blue. And then, of course, we have the measurements as red this time. So the simulations are black and blue, and the measurements are red. And as we see to the right, we have the surface elevation going through with time as the submerged landslide slides along the bottom of, or downhill of the bottom. And we see the development of a wave. And we see that the mic-free, the blue model that has the hydrostatic assumption fails quite miserably to capture the red surface elevation developed by this submerged breakwater. But we see that actually the mic-free wave FM module captures the surface elevation quite accurately, and that has been introduced by this submerged breakwater, or sorry, submerged landslide, of course. So we see some of these development of the wave and the nonlinear transformations and dampening is actually encaptured by the model. Then we are looking into now the porosity setting of the model. So in order to investigate this, we are running it through the porous dam break scenario. Here we had an initial water column to the left. Then we had a wall separating the water from the porous area. And then to the right, we have an empty reservoir. Then at time step, I believe 0.5, it takes 0.5 seconds to pull out the separator between the initial water column and the porous dam break scenario. And here we can see how the HLLC Riemann solver performs, trying to simulate this discontinuity. And we also see how the Darcy-Forchhammer implemented porosity setting performs when the water flows through this porous media. So if we look into the time series to our right, we see that initially there's a quite abrupt cut in the surface elevation. Of course, this is included from the impermeable separator between the porosity and the initial water column. Then we see as we remove this, we see the water slowly running through the media, and we see that the surface elevation or the head loss between the two positions is actually is leveling out, and we see that after 2.2 seconds we have some steady flow throughout the porous media. But we see that throughout these processes, actually the microwave FM module is capable of simulating this porous flow through a porous media, and it captures it accurately, quite accurately. So this tells us that actually the porosity model that we have implemented can be used and validated, or can be used to model some of these porous areas such as breakwaters. Now I've been talking a lot about these breakwaters and overtopping, but let's see how it performs against some measurements. Here we have a model test from Bruce Tan van der Meer, J.W. Franco, and Pearson. And we have also compared this against some open foam investigations by Bjarne Jensen, Jacobsen, and Christensen, 2014. Here we are considering a typical multi-layered porous breakwater where we have a filter, an armor layer, and a core. And let's just jump right into it. So let's see, yeah, 1 second. So first off, we try to model it using a non-porous setup. And we see that the experiments and the microwave FM, so experiments are white dots, and the empirical relations are with a black line, and then the experiments or the microwave FM results are with black squares. And we see that actually the microwave FM module captures in this scenario, even though it is and non-porous setup, it actually captures the values quite accurately. Then we went on to a porous slope, and here we see performance is still quite good compared to the dimensionless freeboard and dimensionless overtopping discharge. Here we had increased the vertical discretizations to 30 vertical layers. And we have a slight underprediction, of course, when we had short waves, which is to be expected, as these are quite difficult to try and model. So now we've seen that it can actually happen, or it is capable of resolving wave breaking, run-up, and overtopping. So it can actually also, we have had some experience, but I can see that I'm not running out of time, but I should hurry up a bit. We can see that it has been used in coastal flooding studies. So here we have an area in France where we had some large waves overtopping up, and we see the cars being hit by these large waves. So this is actually something that microwave FM is capable of simulating some of this coastal flooding. And of course we can't, as we see in this picture, we can't resolve this spraying, but we can resolve the green water overtopping, which comprises of most of the overtopping discharge in any given scenario. That is also the one that causes the most damage. So let's look into another coastal flooding study in France. That is in Cabreton, in southwestern France. This location is exposed to storm events. There have been reported some storm surges, some overtopping cases in this channel that we are looking into with the bathymetry on our left. What mic-free wave FM is capable of is overtopping happening parallel to vertical walls. So something that the overtopping manual Eurotop actually can't really consider. That is something that we are able to resolve using this mic-free wave FM module. So we can see up to our right that there's been a wave that is propagating along the channel, and we see that it overtops parallel to the size that it is propagating through. So that is some cases where the overtop manual can't really or don't have guidelines for. Also to our bottom right, we see some time series of the accumulated discharges across the two cross sections that we had. So we can see that there are, as of course you can also see the highly nonlinear effect of overtopping, where we have a small or a few waves being responsible for most of the overtopping. Yes, so we can see that this model can actually be used to simulate entire coastal flooding areas, and you are modeling the entire domain as is, more or less. So you are not trying to do any boundaries between the beach and the water domain. Here you can actually represent the landmass as bathymetric features and just let the model handle the overtopping and the rundown of the waves. So you don't have to draw these lines along the beaches and the channels. You can model those as bathymetric changes within the model. Another coastal flooding study in Saint-Malo in France that has also been used before in April. Here we are considering a Saint-Malo where we have a coastal flooding assessment risk study. We have waves coming from the northeast, and they are been propagating through the domain and hitting the beach, where we have then used the Eurotop manual to try and come with some approximations for the overtopping. Otherwise, I think I will try and wrap out this session. I would say thank you for your attention, and you are welcome to contact me with any inquiries or questions relating to the mic-free wave FM module. I would be happy to answer them to the best of my capability. And if I can't answer them, then I will make sure that someone answers your questions. So thank you for listening to me and hearing me out. And finally, if you are interested in the mic-free wave FM module, then please go to our webpage as well. And here you will be able to download the module.